Which alkene would you treat with a peroxy acid in order to obtain the following epoxide? All right, so a peroxy acid, just quickly before we start trying to solve this problem, is a carboxylic acid with an extra oxygen, essentially. So something with this general formula. So you have an R group, and if it was a carboxylic acid, we would just have OH. Since we've got three oxygens, here is where the extra oxygen is. So that's the general structure of a peroxy acid. And one common example that you will see is MCPBA, and that stands for metachloroperoxybenzoic acid. So let me draw the structure of that. So here's the portion that makes it a peroxybenzoic acid, and metachloro means that you have a chlorine on the third carbon atom. We don't need to worry about that at this point, but it's nice to know what this acronym stands for when you come across it. But the most important thing is that that is a peroxy acid, and if you have an alkene, you treat the peroxy acid, you're going to form the epoxide. And so the reaction mechanism when you do this is concerted. So it is a concerted mechanism, which means it takes place all in one step. And although we don't need to know the mechanism, knowing that it's concerted and it takes place in one step tells us one really key thing, that the stereochemistry of the alkene is conserved. And so with that information, it gives us a really easy way to figure out where our alkene was. So we can clearly see the two carbon atoms that form this alkene. And if we want to figure out what it was, here's the easy trick. So notice I've got a pencil now. I am going to redraw this structure. Okay. All right, so we've got the structure redrawn. So we know that the stereochemistry of the alkene is conserved, which means that this stereochemistry that we're seeing in our epoxide came from the alkene. So here's how we're going to do this. These two carbon atoms of the epoxide is exactly where that alkene was. So we are just going to simply erase that epoxide and replace it with an alkene. And now it's kind of ugly looking. Let's fix these bond angles. These are sp2 hybridized carbons, so we typically represent those as being trigonal planar. So let's go ahead and redraw that. So here's our alkene, and what this is telling us is that the hydrogen and the ethyl group are on the same side of the alkene. So hydrogen, ethyl group on one side, and these two methyl groups are also on the same side. And so whether you chose to put the hydrogen and the ethyl group on the top and the methyl on the bottom, or vice versa, it's the same alkene. And we should recognize that that structure is the same as structure B.